Hello, Math 10a. Today we'll be working an example from section 4.5 of the textbook, and this is problem number 220. So the problem asks you to do this. It asks you to sketch a function, we'll call it f, on the interval from -3 to 3 with the following three properties. Firstly, f has local maxima at the x-coordinates plus and minus 1. The second is that f has to be concave up for all x. And the third condition is that f should be positive for all x. And the reason why I really like this problem is because frequently in calc problems you're given a function and you have to determine its properties. And this question is really the opposite. You're given the properties of a function, you have to give an example of such a function that has these properties, which is pretty cool. So the problem is asking us to sketch the function. Let me draw on some coordinate axes and we'll get started. Okay. And we're working on the interval from -3 to 3, so I'll draw those points in as well. And now we can get started. Probably the easiest thing we can get out of these three conditions is to look at the third one, which says f is positive for all x. What that means in terms of our sketch is that if I draw on the line y equals 0 here, then that means that the graph of f, if f is to be positive, has to lie in this region above the line y equals 0. So when we go and draw on our graph, it better lie in this region, or else we'll have some problems. Okay, and now what else do we know? Well, from the first bullet point here, we know that f has local maxima at the x-coordinates plus and minus 1. So let me draw on those x-coordinates. Here we've got -1 and 1. And let's just place some points for our local maxima. So maybe the first local maximum is here, and maybe the second one is a little lower over here. And the point is that these are going to be local maxima, but not necessarily global maxima. And so to figure out what we have to do for the rest of the problem, for the rest of the sketch, is really to figure out how to connect these two local maxima and then draw from them out to the boundaries over here and over here. So let's think about how we're going to do that. I think we should probably start with the local maxima and figure out what the graph looks like, at least around those points. Now you know from your reading that x equals c is a local maximum. And this also holds for local minima. That means that x equals c is a critical point for f. In other words, the only candidates for local maxima and minima are the critical points. And in particular, what does it mean for x equals c to be a critical point? That means that f prime at c is either 0, in which case we have a horizontal tangent line, or the derivative at c does not exist, in which case we get something with like a sharp corner. Okay, so we should probably figure out which one of those cases happens at these local maxima. In other words, do they look like that, or do they look like that? And to figure that out, we can use the second condition of f being concave up. So what does it mean for f to be concave up? Well, if f is concave up for all x, then that's the same as saying that the second derivative of f is positive for all x, at least wherever it's defined. So in other words, if my function has a corner, I won't have the second derivative won't make sense there, but at least wherever the second derivative is defined, being concave up means that the second derivative is positive. Okay, but what does this mean in terms of our critical points? Well, think about what the second derivative test says. The second derivative test says that if x equals c is a critical point, and if it happens to be of the form f prime of c equal to 0, and if the second derivative is positive at x equals c, in other words, if the graph is concave up at x equals c, then what does it tell us? Here the second derivative will tell us that x equals c is actually a local minimum for the graph, for the function. And the picture here is, well, imagine that this is your critical point. You know you have a horizontal tangent line. If the graph is concave up around this point, then it looks like a cup, right? And so in that sense, you can see that this point here has to be a local minimum if this is to be true. So what does that mean in terms of our graph? Well, we have these local maxima, and because they're local maxima, they're also critical points. And now the second derivative test is saying that if they're critical points of the form f prime of c equal to 0, and if the second derivative is positive there, then it's actually a local minimum. So what that's saying is that these critical points have to be of the form f prime does not exist. In terms of what the graph looks like around those points, remember that points where the critical points where the derivatives not exist, they tend to look like cusps here, or sort of peaks, you know? And so what I'll do is I'll draw these peaks in here. And now all that really remains to do is to just fill in the rest of the graph between these two critical points and up to the boundaries -3 and 3, while making sure that the graph is still positive and concave up. And so to do that, I'll just draw in the middle section so that the graph is sort of cup-like. And then I will do the same on the right-hand side up to the boundary. So maybe it looks something like that. And maybe on the left-hand side up to the boundary, it looks something like that. And so you can see that we've drawn a graph that has the specified local minima at plus and minus 1. It's definitely concave up, and it's definitely positive. And so the reason why I really like this exercise is because it gets you doing a lot of things. It's got you thinking about local extrema, it's got you thinking about the critical points, what the form those critical points can take, how the concavity relates to that, the second derivative test. And like I said before, it gets you reversing the equation here. You've got to produce the function rather than deducing its properties. So I think that's really cool. So I hope this was very helpful, and thank you for listening.